Welcome to the complement of Lecture 8 on the category of vector spaces, titled Existence of Bases. In this lecture, I want to answer a very important question. Does an arbitrary vector space admit a basis? We've seen in Lecture 8 that if your vector space is finite dimensional, that is, if it is a linear span of a finite subset, then indeed it always has a basis. What about a general vector space that does not necessarily have a finite spanning subset? And it turns out the answer depends on the axioms you choose for set theory. So, as I'm an analyst, I will typically work within the axioms called ZFC for Zermelo-Frankel plus choice, and that means in particular that I admit the axiom of choice as part of my set theory. It is known that there is no contradiction that arises by adding the axiom of choice to the basic axiom of Zermelo-Frankel of set theory. Now, without the axiom of choice, actually it is impossible to answer the question whether an arbitrary vector space admits a limit. And the reason is that there are models of Zermelo-Frankel where all the vector space have a basis. Any model of ZFC would do. But there are also some models where some vector spaces do not have a basis. And indeed it is known that if all vector spaces have a basis, then the axiom of choice must hold. So what this means is that if you have a model of ZF or Zermelo-Frankel where the axiom of choice is actually false, for instance, a model where instead you choose the axiom that every subset of the real line is measurable, then there will be somewhere a vector space which does not have a basis. So this is an important observation that certainly this is a non-trivial question, and in fact, all vector spaces admitting a basis is equivalent to the axiom of choice. Now, let me prove to you that under the condition that the axiom of choice is indeed true, then all vector spaces do admit a basis. I'm going to follow a strategy that is very similar to what we did for finite dimensional vector spaces in Lecture 8, but this time we will have to invoke the axiom of choice to get the result that we desire. So let me remind you first of all, of course, that a basis of a vector space is a subset of that space which at once spans the entire space and yet is linearly independent. And we showed in Lecture 8 the following very important theorem. It states that essentially bases are maximal linearly independent subset. To be more specific here, let V be a vector space which is spanned by one of its subset called S, and let L be a subset of that S which is linearly independent. Then we consider the collection script L of all B subset of the spanning set S, which contain L and which are linearly independent. And the following two assertions were shown to be equivalent. 1. B is maximal in that script L for the inclusion, and 2. B is a basis for the vector space V. We use this exact result to show that if V is finite dimensional, that is, if you can choose S to be finite, then indeed there exists a maximal element in the script L set, and therefore there exists a basis. The question is, without assuming that we can find a finite spanning set S, how do we obtain the existence of a maximal element of such a family of linearly independent subsets? To that end, as I said, we shall use the axiom of choice. Again, as an analyst myself, I usually use the axiom of choice in an equivalent form called the Zorn's lemma. The Zorn's lemma is actually a result about finding maximal elements of sets. It says the following. Let E be a non-empty set with an order relation. If every totally ordered non-empty subset C of your set E has an upper bound in E, then E actually has a maximal element. So the set E is not assumed to be totally ordered. That is, it is possible that two elements in E cannot be compared. Neither is greater or equal than the other. However, what this theorem says, which is very strong, is that if you take a totally ordered subset, that is, a subset C where indeed any two elements of C can be compared for the order on E. And if that subset C has what's called an upper bound, that is, there is an element in E that's greater or equal than everything in C, then E has a maximal element, that is, an element X in E, so that if Y is in E and Y is greater or equals than X, then Y actually equals X. Zorn's lemma is equivalent to the axiom of choice. It is an interesting proof, and it is a very common tool in topology and analysis to find maximal elements. It is actually at the core of some of the most important results in infinite dimensional analysis, such as, for instance, the Hahn-Banach theorem, or at the core of some of the most important results in topology, such as, for instance, the Tikhonov theorem. Now, a problem with using Zorn's lemma is that it does not provide us with a mean to explicit any maximal element. Thus, a proof based on it gives an implicit argument, as removed from a constructive argument as it can be. It means that, sure, by Zorn's lemma, if you prove that you have a non-empty ordered set with the property that every totally ordered non-empty subset has an upper bound, then you can conclude that you have some maximal element. But nowhere in the proof of Zorn's lemma is there any hint as to what that element could possibly be, because it invokes the axiom of choice, which, again, does not provide you any hint as to what the choice function would be. So here's the main theorem of this lecture. It states informally that every vector space has a basis under the assumption of the axiom of choice. Specifically, if V is a vector space over a field K, and if L and S are two subsets of V with L linearly independent and S spanning the whole space V, and if L is a subset of S, then there exists a basis for V, which contains L and is contained in S. The proof of this theorem follows a strategy similar to what we did to prove the existence of basis in finite dimension in lecture 8. Let script L be the collection of all the subsets of S which are linearly independent in V and contain L. First, note that L, indeed, is an element of script L, so script L is not empty. Then let script C be a subset of script L, be chosen such that it is not empty and it is totally ordered. Let M be the union of the elements of script C. Note that M is therefore a subset of V. I want to prove that this M is an element of script L and an upper bound for script C. So first, let's prove that M is indeed linearly independent. Let V1, etc. Vn be a subset of M, and T1, etc. Tn be scalars, such that T1 V1 plus T2 V2 plus etc. plus Tn Vn is equal to 0. Now we know by definition of M as the union of the element of script C that for each j between 1 and n, there must exist an element Cj in script C such that Vj belong to Cj. Now, on the other hand, script C is totally ordered, so it means that we can decide of the set C1, C2, etc. Cn, which is the largest for inclusion. So that means we can in fact find a j between 1 and n, such that for all possible k between 1 and n, C sub k is a subset of C sub j. So in particular, the set V1, etc. Vn is a subset of that C sub j, that largest among the collection C1 to Cn. And we know that any element of script C by definition is also an element of script L, which means in particular that it is linearly independent. So we have written a linear combinations of vector of a linearly independent set, which equals to 0, and we can conclude all the coefficients are 0, which means here T1 equals to T2 equals etc. equals to Tn equals 0. And therefore, we have shown that M is indeed linearly independent. Now it is immediate that L is a subset of M, and that M is a subset of S, because this property is shared by every element in script C. It is also immediate by construction that if you take an element C in script C, then it is a subset of M. That is simply a corollary of the fact that M is a union of the collection script C. So what this means, as you can see, is that big M is an element of script L, and it is larger than any element in script C for the order, this is the inclusion here. So in other words, it is an upper bound for the collection script C. Now by Zorn's lemma, we can conclude that there must exist a maximal element for L. Let's call it B. What do we know about B? Well, as an element of L, we know that it contains L, it is contained in S, and it is linearly independent. To conclude the theorem, it is sufficient to show that B spans all of V. Let's suppose it doesn't. Now note that, on the other hand, S spans all of V by assumption. So if all of S is a subset of the linear span of B, then the linear span of S would be a subset of the linear span of B. But of course that would mean that the linear span of B should be the whole space. So we can conclude that S is not a subspace of the linear span of B, and therefore there exists a vector, let's call it V, which is in S but not in the span of B. Since B is linearly independent, we conclude that B union the singleton V is also linearly independent, because if it wasn't, then V would be in the span of B. But on the other hand, since V is not in the linear span of B, it certainly isn't in B. So in particular, the set B union singleton V strictly contains the set B. It is strictly greater for the order inclusion. Now on the other hand, L is a subset of B, so certainly L is a subset of B union the singleton V. And since V is in S and B is a subset of S, B union the singleton V is still a subset of S. So we have all the necessary properties to conclude that B union the singleton V is actually an element of script L. It is a linearly independent subset of our vector space, which contains L and is contained in S. Since it contains B strictly and yet B was assumed to be maximal, we have a contradiction. So since B is maximal, the construction I've just done cannot happen, which means that V must be the linear span of B. So B is a basis for your vector space. An immediate corollary is that every vector space has a basis, whose proof, as usual, is done by applying this very general theorem to the special case where the linearly independent set L is the empty set and the spanning set is just V. Here we do not need to work with a spanning set that is finite like we did in finite dimension, because our maximality argument does not rely on cardinality of finite sets, but rather on Zorn's lemma. So now that we have shown that indeed under the assumption of the axiom of choice every vector space has a basis, let's discuss a little bit more the consequences, if any, of this theorem. First, I will give you a definition. A vector space V is infinite dimensional if it's not finite dimensional. And there is an immediate consequence. A basis for an infinite dimensional space must be infinite, because if it was finite, a basis in particular is a spanning set, and therefore your vector space would be spanned by a finite subset, which means it would be finite dimensional. So automatically an infinite dimensional vector space can only have infinite bases for sure. Here is an example of a reasonably easy infinite dimensional vector space. It is the space of all polynomials over some scalar field, let's say R, which has a basis which is given by 1x, x squared, etc. It's an infinite basis. You can check that it is spanning. That's the definition of a polynomial. By definition, a polynomial is a linear combination of those various powers of the indeterminate. But it is also linearly independent, and that can be checked again very easily because the coefficients of polynomials over R, for instance, are unique. So the only way you can get to polynomial 0 as a linear combination of these powers of the indeterminate is by having all the coefficients 0. It is a canonical basis for this vector space of polynomials. Of course, this could be easily generalized by considering instead a countable family of polynomials, P sub n, indexed with n ranging over the natural numbers, with the property that the degree of P sub n is n for all n in a natural number. That's easily checked to be a basis again. So in this case, certainly infinite dimensional spaces can be handled using bases, and so infinite bases can be useful. But on the other hand, here, of course, we have an explicit basis. so we did not need the full power of our theorem. But in practice, it's not very helpful to work with such bases for many spaces of interest, with infinite bases for many spaces of interest. A simple little brain twister is to try and figure out what could possibly be a linear basis for, say, the space of real-valued continuous function on the closed interval 0, 1. And you'll quickly realize that it's not at all clear what such a basis should be, and in fact, owing to result from analysis, such a basis cannot be countable. It has to be infinite uncountable. And in fact, this is a case where it would follow from our work here that such a basis actually exists, but we have no idea what it is. So to handle situations where we play with infinity, it is often helpful to introduce some sort of tools, and I am of course biased here, but the tools that I think is particularly helpful is analysis. In analysis, we can introduce a notion of limits. The limits are the sort of tools you can use to deal with anything with the word infinite in it, or infinitesimal or infinity, as really they allow you to approximate, quote-unquote, these notions with maybe more finite notions, such as, for instance, we can make sense of infinite sums as limit of finite sums, or in other words, we can make sense of a sort of generalization of linear combinations where we would allow infinitely many vectors and infinitely many coefficients, of course under certain conditions, and that would be in some sense the limit of normal linear combinations. And if you do that and you have the right notions, you might be able to allow for new notions of bases that are not the one we have been discussing in this lecture, where you could allow for certain type of infinite sums of vectors. And examples include Schauder bases, and maybe most importantly, Hilbert bases, as used, for instance, in Fourier analysis. Now, I'm not going to get into this explanation in this lecture, because this would require me to introduce topologies on vector spaces so that I can indeed talk about infinite sums. But it is a good place to remind you of something that has been stressed all throughout our lectures, but maybe here takes a particularly salient meaning, is that linear combinations of families of vectors are always finite sums of multiples of various vectors. So in other words, so even if, like for instance, in the case of polynomials here, we have an infinite set 1x, x squared, etc., that's a basis. In particular, it is a spanning set, but what that means is that every polynomial is a finite sum of scalar multiples of some finitely many of those elements in that infinite set. If you look at all the proofs we do about linear independence, even if we're working with an arbitrary set that we want to show is linearly independent, we always take a finite subset of it, arbitrary, such that we have a linear combination of those vectors in that finite set that is 0, and then we proceed. So the idea is that when you do only algebra, you can only do finite sums. We know how to make that. If you want to talk about infinite sums, then you need to introduce a notion of limits. So this is why, in practice, it turns out that outside of a few special cases, bases outside of finite dimensions are often not that useful. They do allow you to define linear maps, just as we proved in lecture 8, and I can let you do that as a little exercise that you can generalize the result very easily, and that's because in lecture 8, we proved an isomorphism result in full generality. However, the resulting maps may be very difficult to handle. In particular, if you start introducing the notion of analysis on a space, that is, you put a topology, one of the questions you will want to answer is, are my linear maps continuous for these topologies? Are they playing well with that structure? And it turns out that the answer is usually no, or at least I don't know, when you make these functions out of arbitrary bases given by the axiom of choice. So it is an interesting observation from set theory that indeed we can talk about bases of arbitrary vector spaces if we are willing to work in the right model of set theory, but it is not actually a very useful tool outside of this observation, certainly nothing like what we are going to do in finite dimension where bases are fundamental. And this concludes my complement to lecture 8, discussing bases in full generality.